Right, Freddie, how are we doing this morning? Morning,
Um,
afternoon, more like just hitting the cusp of it. Yeah, thank you for being flexible today. It completely slipped off my mind
that's all right.
that there was an appointment made. One of those things, the diary's getting packed by the day, and the more
Yeah,
I get to update it. So thanks for that. Yeah, cheers for that. Right, okay, good. How's it going over your side? Just a quick check-in. How are you doing? And yeah, how's it all going revision-wise?
yeah, it's good. I'm just trying to balance subjects right now. To be honest, that's what I found. That's to be fair, that's what I've found most difficult in this
Yeah.
revision process.
Yeah,
Is actually just balancing my subjects.
yeah. How many? Because you're doing maths and further maths and physics. Any other subjects?
Yeah, I'm doing music as well.
Oh
But
wow, I didn't know that. Okay, you're into your music. I didn't know that, pretty.
yeah,
Right.
yeah.
What instrument do you play?
I play the piano and the saxophone.
Oh, piano and saxophone. Fantastic. Very classy. Right. Brilliant.
Yeah.
I'm I'm a guitar player, but I also
Oh,
play,
nice.
yeah, a little play. I play a little bit of organ as well, and
Oh, that's cool.
bass as well. Yeah, yeah. So I'm
Nice.
well into music. Good to know that you're into music. Yeah, I used to be a semi-professional musician and
Really?
done some collaborations. Yeah, with some musicians down in France when I used to live down in London. That's when I did most of it. But I still write songs and such. So
Yeah. What
and
what what kind of style is it you write?
it's a bit of a kind of folky, kind of reggae, kind of country, kind of, but lots of different mixes though. I've played with lots and lots of different musicians in the past, and some of it has also been experimental. So
Yeah.
not quite within genres, but try to create a genre.
Yeah.
Try to fuse some Eastern music like the Indian type Bhangra and indie, yeah, with
Cool.
some jazz and funk. So
Yeah.
tried to create a genre with that. So worked on that with some friends back in London. But we're going a few years back anyway here. But you know, I'm still musically active in terms of writing music and playing when I can get a chance. Good stuff. Brilliant.
Cool.
All
Yeah.
right. Okay. Right. Back to the not so as exciting as music topic, because you know music is art, and they say art is the foundation of civilization. So before we had physics, before we had all these things, we had music. So
Yeah.
I'm quite passionate about that. Okay, away from our passions to our second passions. Right, a very quick one for us to start with. How did you get on, by the way? Oh yeah, I was going to give you some advice as well because you said you're finding it hard to juggle the subjects and such.
Yeah.
Sometimes what can be really helpful in helping with that is doing like a rotation. So having short chunks of concentrated revision, but then rotating it with different subjects. So you do like 30 minutes, you know, not really more than 30
Okay.
minutes of say physics. Yeah.
Yeah.
And a topic that you've not covered in a while, you know, pick a topic question, you know, you can go to physics and maths to so many sources, even from a textbook if you wish to. Yeah. Go through that for 30 minutes concentratedly, take a break for, I don't know, 15 or so minutes, and then go and do a very similar thing, but 30 minutes for further maths. Yeah, taking
That's
the break.
yeah.
So like you're rotating it in that way, you keeping, you know, each subject is being visited in a
Yeah.
concentrated manner. Because I think sometimes what happens is, and I fell foul to it as well, is that you know you may like one subject more than the others,
Yeah.
and then you end up spending half a day just on the subject you love, you know, and then the others start falling out of sync a little
Yeah.
in terms of how much
Yeah.
revision you're putting into them. So I then changed my strategy because then when I went to university, and I'll tell you one thing that Cambridge is a pressure cooker, well, like Oxford is as well. So within 6 months, the amount of topics that you'd have done, it's a lot. I mean, it's bundles of files full of work, and
Yeah.
to try and balance all those modules was very, very difficult. And so for my revision, I had to then adopt that tactic of, rotating through as you go through the day, just to make sure that everything is visited. And then I found that helped me create a balance, which was right, to be able to be on top of all the modules. So that's probably something worth trying to do. Yeah. So short bursts of revision, break, but rotating through your subjects, that might be helpful. Try that for a bit, see how that works. Yeah, because different things work better for different people.
Yeah.
Okay, cool. Right. So I thought we'd just start off with a radioactivity question, just a warm-up question, really, more than anything. And this is just calculating activity for this particular one.
Okay, cool.
Good?
Yeah. Is it B?
Well done. Excellent. Good. So very good. So there's a lot in here. So just to go through your method then. So you found the number of particles, because your formula would have been A equals lambda n. So you needed to work out the number of nuclei. So then to find the number of moles, it's the mass over the molar mass. Now the molar mass here is this 226. Yeah. So then you'd say 3 divided by 226, which gives you the number of moles. And then you took the number of moles, 3 over 226, and you multiplied this by Avogadro's constant. And this gave you the n, which you were then able to use in there. Is that correct?
Yeah, that's sort of what I did when I did the mass. I did so I did 3. I converted the 3 grams to kilograms.
Okay, good.
Divided it by 226U.
Ah, I see. You're absolutely right. You can do that. You are You were absolutely within your right, and very, very, very good thinking actually there. So here, that is what the method you've used actually, Freddie, is the right thing that you'd have done here. So you change this to kilograms and then change that as well to kilograms. That is the absolute correct way, but a little shortcut here, and it's a shortcut method.
Yeah.
This value, which is the relative atomic mass, yes, this is relative. It's relative to 1 atomic unit. You following that?
Yeah.
Relative to 1 AU. Good. So generally, yes, if you wanted to work out, and 1 AU, which of course we know is 1.661 times 10 to the minus 27 kilograms, the other way that you can do it as well to work out the number of moles, you can think about this relative atomic mass as also being, each of these will be relative. You can make this, think about this as being relative to the atomic unit as well. But what I mean is in saying that it's very, I'm almost finding it tricky to say, to explain properly. The other way that you can do it, let me just say it simply, is to, if you don't want to go through the atomic unit a process that you used, is to simply think about this as also being in grams. That's another way. Now, this method is more common. It's more common in chemistry. So in chemistry, whenever you're given values and you need to work out number of moles, the authors give them to you in grams.
Yeah.
So that you can then use the numbers directly as they are in the periodic table. Okay, so that's another way, but there's no harm in what you did where you convert this into the kilogram version and also converted that into kilograms, because you still get the same answer. Yeah, so now for the lambda, you used ln 2 over t half, and then the t half, did you then change that into seconds, I take it?
Yeah.
Very good, spot on, absolutely spot on. Good, excellent. This was not an easy question, so I'm very impressed that you got it, and you got it in good time. Well done, excellent stuff. Right, so it seems you've definitely got a grasp on these calculations with half-life. It seems so. Do go through the questions when you get a chance, the ones I sent through yesterday. Did you get a chance to go through any of them?
No.
No. Okay, when you get a chance today, you have more of a bigger afternoon today anyway.
Yeah.
Right. So just to pick up pieces from where we left, and we were looking at uses of radioactivity. So we looked at carbon dating, we'd also looked at argon dating, and we'd looked at uranium lead dating. Another important part, by the way, I'll apologize in advance that today will be content heavy. Yeah, so that we can cover ground, and then if we've got some time at the end, we'll go through some exam questions, but it will be content heavy. Stop me if you've got a question at any time. All right.
Yeah, sure.
Super stuff. Okay, cool. So we'd also looked at uranium lead dating. Another use is in radioactive traces. Do you remember encountering anything about radioactive traces? Or learning about radioactive traces?
No.
Okay, so radioactive traces essentially allow us to monitor the passage of a substance through a system. That's what it does. Okay, so allows.
Yeah, is this where you put it into like the bloodstream or something? You can see it go around.
Yeah, you're absolutely right. You're absolutely right. You're absolutely right. Allows monitoring of a substance as it flows through a given system. And you're right, you mentioned tracing in the human body, yeah, but also we've got tracing that happens in plants to see uptake of certain minerals and such. Now, the key thing is we need to know what features an ideal radioactive tracer should have. So, ideal tracer what do you reckon would be some of the ideal features you'd be looking for in a tracer?
Can you say like non-ionizing?
Well, unfortunately, all radiation by its nature is ionizing, the least being gamma, though. It is ionizing, but only to a small extent. So think about something that was, say, if it was being used in a person's body. What are some of the precautions? What are some of the things you might consider before injecting that tracer in them? Well, for one, you want to be able to detect it on the outside, isn't it? You want to detect it on the outside of the body.
Yeah. So it has it can't travel out of the body. Like,
yeah.
So it can't penetrate through the body.
Yeah, well, yeah. One of the things is you mentioned something very important there, which was about the ionizing capability. So you don't want it to be very ionizing because, of course, it's going into somebody's body, and if it's very ionizing, it'll be essentially like essentially you can think of alpha particles as little mini bullets that will be going through the person's cells. So they will damage the person's insides and internal organs, and they will create an acidic environment, which again will damage cells. Yeah, and in addition to free radicals. So you mentioned something there. So ideally, you don't want it to be an alpha particle source. Does that make sense?
Yeah.
Yeah. So you want it to be beta or gamma. Now, the advantage, of course, is the less ionizing. What about the other advantage? What other advantage can you think of? Something that's a beta or a gamma source.
They're smaller. Well, it doesn't really make a difference actually if they're smaller.
Yeah, emit alpha, sorry. Beta or gamma.
Well,
so just to give you an idea of what happens. So if this person has got this tracer running through the system, injected through the system, and they want to monitor, say, the functioning of a particular organ, what they do is they then take a camera. Now, this is not your usual camera. So if the tracer is a gamma emitter, then this here is what we call a gamma camera.
Yeah.
Because remember, gamma will pass through, so then they can make an imaging of what's going on or the uptake of whatever particular substance they're monitoring through the person's body. So you want the source, you want the tracer to be able to emit out of the body. Now, beta or gamma, well, especially definitely will pass through the body. Okay, so it allows for imaging. Whereas alpha would not pass through because alpha, remember, is stopped by skin. So alpha would not pass through. So the other advantage to think about here is that so it can be detected on the outside, because you want to be able to detect it. Make sense?
Yeah.
Good. What about half-life considerations? What might you say about that?
Yeah, so
long half-life, short half-life?
You'd want a relatively, or you'd want a, would you want a long half-life?
Yeah, okay. So if we had a long half-life might seem, and I think we're not being very specific here because we're being very, words being used are quite subjective, long and short. What do I mean by long? What do I mean by short? But in answering your question, if we say long, obviously then I'm taking it that you're saying it should be long enough so that the measurement can be taken. That's where you're coming from, isn't it?
Yeah. Because
if it's very short, it's not going to get time to actually reach the target organ. It would have decayed. Yes. So in a way, perhaps to phrase it better, we might say that the half-life must be short enough, to allow measurements to be taken. Now you can say long enough here or short enough, but I'd say short enough to try and say that we would try to minimize any extra dosage or the need for the tracer to be in the person's system longer than it should be. That makes sense, right?
Yeah.
Must be short enough to allow measurements.
Is it?
Yeah.
Is it dangerous to have particles decaying inside the body?
And it all depends on how much dose, because remember, everything we're eating already is quite radioactive to some degree anyway.
Yeah.
Yes, but the doses we're receiving are very, very, very minor dosages. Now, do you remember Litvinenko, the poisoning that happened to the Russian
Oh yeah.
spy? Yes.
Yeah.
So that poisoning was via radioactive poisoning, and plutonium itself was what was used. Now, plutonium emits alpha, beta, and gamma, so it would have been the emissions that actually killed him from the inside.
Yeah.
Yeah, so that dosage, even though it was small enough, I mean, we're probably talking, we're talking less than a teaspoon. I mean, to the point that he couldn't detect it while drinking it in his tea. So there's a very, very, very small dosage, but lethal enough. So the dosages we get are nowhere near that. Yeah. So yeah, absolutely right in answering your question. It is absolutely lethal, because in a sense it's very hard to treat it, because even the doctors trying to flash it out would have to wear certain suits to operate. So the operation itself is no easy thing at all. Yeah. So the sources we normally use will have short half-lives, maybe approximately of about, say, 6 hours if something is going to go into somebody's body. Yeah.
Yeah.
That after 6 hours, then, and because of the small dosage that you received, you know, by the time it's 24 hours, that's gone through 4 half-lives. And if you recall, yesterday we did that exercise looking at, for example, the percentage of carbon-14, and we realized that after 40,000 years, which was like 8 or so half-lives, there was less than 1% of it. So, you know, after about 48 hours, you pretty much have near nothing of that tracer that was placed in your body.
Yeah.
That makes sense, right? Okay, great stuff. Other applications, again, the only reason why we have to go through this is because they may ask 6 markers for you to make mention of some of these points we're making here. So other industrial uses, yeah, and this is detecting engine wear. Okay, I should say detecting extent of engine wear. I'm going to put it that way. Okay, so what makes engines move normally? We have things rotating, and also we have these things called pistons, right? Heard of pistons?
Yeah. Excellent,
brilliant. So pistons, of course, are the moving parts that actually lead to rotation of the moving parts. Now, in a piston, because of these moving parts, there's often wear and tear. So what normally has to happen is that the engineers need to be able to predict the extent of the piston wear and whether then the machine is safe. So to do that, what they do is they take a ring. So if you like, you've got a moving part that's going into another moving part. Yeah. So they'll have a ring. Now this ring here, so this is this part, that's the inner part of the piston, if you like. So this moves up and down inside this barrel. Yeah.
Yeah.
And by using a radioactive ring, this ring will wear out. Now, when it wears out, the metal pieces or shreds of them end up in the oil. So this here would be in oil. And this here is movement of piston. By measuring the amount of radioactivity in the oil, they can work out the mass of the piston that has eroded off. Does that make sense?
Yeah.
Yeah. So this is a ratios problem, similar to the problem you had in one of the multiple choice, saying, you know, a certain amount of water gets poured out of a liquid, and what was the volume of the liquid? Remember that question?
Yeah.
Yeah, excellent. So same type of very similar calculation. Okay, so it's a ratios problem because they know that at the start, the oil would not have been radioactive at all. Okay, so that's one application there. Other applications include, so we spoke about looking at uptake of iodine in the thyroid. Okay, so the thyroid normally controls things like metabolisms, and it functions better when it's got iodine, so to speak. Okay, and some people have got a shortage of iodine, so they might be less active, or sometimes some people have got more iodine, and so they are what we call hyperactive. So to monitor the uptake of how well your body is utilizing iodine, doctors would involve a tracer, or put in a radioactive tracer. Okay, now this radioactive tracer is normally sodium iodide tracer. You don't need to know the name, I'm just giving you the detail here. And it's a beta emitter, okay, but it's got a very short half-life. Beta emitter. Okay, and what they do then is they compare the amount of activity, or in other words, the activity in your thyroid, to an exact sample, yes, exact mass of sample that they would have used from 24 hours. So they wait 24 hours, see what your activity is, and then they compare it to an exact mass of sample 24 hours later that is outside of the body. And then they can look at the data then to analyze whether you are, you know, above or below the normal intake or rate at which your iodine should be working in your thyroid. Okay, another one here is, we mentioned, is monitoring uptake of fertilizers in plants. Okay, now in this one, the fertilizer, what do fertilizers contain? They contain phosphorus. And phosphorus in this case is a beta emitter that they put in there, and it's got a half-life of about 14 days. So that way you don't end up with a lot of radiation in the food when you do eat it. By the way, I didn't mention this, but it's worth just mentioning, seeing as we spoke about it. In engine wear, when you are, the ring itself has to be made radioactive. So how do they make it radioactive? Ring is made, any ideas?
I don't know, just put some radioactive waste on it or something.
Yeah, actually what they do is it's made radioactive by being bombarded with neutrons in a nuclear reactor. Okay, this happens in a nuclear reactor. So what essentially happens is that the nuclei of this metal then become unstable because now they have absorbed an excess number of neutrons. So remember what we spoke about with the strong nuclear force and the distance, yeah? So the nucleus now becomes very big in this ring metal, or the metal atoms, the metal nuclei become very big and they become unstable. So these then start decaying via beta minus emission, okay? So they decay via beta minus because they become unstable. Okay, all right. And another very one that they like to use, I've seen it a number of times, is where they ask a few questions, is detecting leaks in underground pipes. So in this case, they'll either use, so tracer is either beta emitter or gamma. Now, if it all simply depends on the soil properties, the densities, and the depth to which the pipes are. If the pipes are close to the surface, then a beta minus emitter will work. Yeah.
Yeah.
But if they're very deep, then a gamma emitter is what works. Because as you can imagine, so what they do is they would have, so if that's your pipe and there's a leak at some position, yeah, and what they would have is they would have somebody in a little van. And this was actually a job I did in a previous life before when I was a cable systems engineer. Yeah, so there we go. So somebody here with a little detector, and then they wait for where they get largest signal, yes, from the detector. And at that point, they know that's where they've got the leak, and that's where the digging happens. Yeah.
That's quite cool, actually.
Yeah, yeah. Because can you imagine but it was a nightmare when I was working in that job, though, because the moment you find the leak, sometimes you find that the leak is in the middle of a very busy road in London, and
yeah,
it's trust me, it's a nightmare trying to fix something that is underground in the middle of a city.
yeah.
Nobody wants you to start digging, that's for one. So yeah, so that is it. And lastly, last two, you see references to these in the questions I sent you. One of them is thickness monitoring. Okay, so if I've got some material that I am narrowing in thickness, and I want to check that the thickness is right, okay, then what I'll do is I will calibrate my detector. So this is my detector, and I'll have a beta emitter. So I'll calibrate my detectors to say, okay, when the thickness is 1 millimeter, for instance, then this is the activity I'll be expecting here. If I get an activity that is less than that, then of course, then I know that my material is thinner than I wanted it to be, in which case then this can be recycled back and taken into the plant so that it's made to the right thickness. Likewise, if it was greater, then I would detect a drop to the level that we've calibrated it to. Then again, this would probably again go through some rollers again to make it thinner. So that is what thickness monitoring is all about. And this is used to monitor thickness of LCDs, screens for televisions, glass manufacturing, anything where the thickness needs to be controlled. Okay. Yeah. So, and of course, it helps minimize waste and such for industries. And lastly, power sources for remote devices. Ever wondered how satellites and things that are up there stay powered up in space?
Yeah.
Yeah, because they've got no batteries there to then recharge, and you can't use solar panels per se. So what they do is they use radioactive sources. Now, radioactive sources have a very long half-life. Yes. So if you get something that is being powered by a radioactive source with, say, 1 million years half-life, and that is an alpha source emitter, remember that each of those alpha sources, yes, they leave with kinetic energy. So if I have, just to give an example, if I have an alpha emitter, these alpha emitters, and they're encased in a box, these alpha emitters have got a kinetic energy that when they then collide with the walls of the box, that kinetic energy will be transferred, and it will turn into the thermal store. In other words, the temperature of my casing will increase. So I can use this temperature here to create a power source. Okay. Now, so temperature rises and can be used to create a power source. Now, the thing is this, what was I going to say now? Yes. In any device that generates power, yes, as long as we've got a high temperature, we can use that then in many different forms. to form. So if you connect, if you have two junctions, just to let you know, two metal junctions, at different temperatures, you can actually create a potential difference. So it's that kind of idea, just to that you wouldn't be asked to explain this, but just to know that it is used for power sources for remote devices, and they will ask you questions. The questions would generally be based around the formula power equals A times E. Yeah. So where the power is the activity of the source, and E would be the energy of each emitted radiation. And normally, like I said, the source is normally an alpha source because they are monoenergetic. So far, so good?
Yeah.
Very good. All right. So we can also, how else can we rewrite this equation, by the way? We can write it like, oops, P equals lambda NE. Because I've simply said activity there, which is lambda N. All right. Superb. Next thing, we are going to look at the NZ graph. NZ graph. Now, this is one that you need to memorize how to draw. NZ graph. Can you remember anything about the NZ graph?
Yeah, we did it quite recently, actually.
Oh, good, good.
So it's quite fresh, I think. Hopefully.
Good.
We'll see, but.
Fantastic. So if I was to plot it, just give me the directions as to what I'll have to do.
Yeah, so obviously draw the axis, and then.
There we go. So that's my axis.
I can't remember which one's N. That's N?
N, yeah, and that's Z. Good.
Then you can draw. What I do is then you draw like a dotted line, like a Y equals X kind of line.
Fantastic.
And Y equals Z line.
Yes, you're right. I can draw a Y equals X line. You're absolutely right. So if I did, I'm just going to pick a gradient here. That's sensible. So this here is my N equals to Z line. Very good. What next?
Then don't you draw like a so you draw where it's like stable and not stable?
Yeah, you're right. But before that, a key thing to do is you pick a scale. Now, there are instances where they don't give you scales at all, and you have to choose it. And I've seen those. And the instances where they already put the scale for you, nice and easy. So it's worth knowing it from the point of view of all the different intersection points. But you're right, if I've got my N to Z line, that's a good start. Okay, that's a very, very good start. So I'm going to pick a scale because I know that this thing goes all the way, at least in the Z, it goes all the way to about 100. Yeah. So if I pick a scale and I go maybe from there 20, 40, 60, 80, 100. Well, if this is the NZ line, then by virtue of that, this also must be 20. Okay, and if that's 40, there would also be 40. So 20, 40, that looks about even. So it's a rough sketch, but we'll capture what we need to. 60, 80, I'll give it there. And we'll give that about 100. Okay, and we're gonna go to about 120. We can go all the way to 140. Now, the heaviest isotope we've got is uranium-238. Yeah, so if I've already got 100 this side, there's not much point going past 140 on this side. Make sense? Because 140 plus 100 is 240, and we know that's going to be below that. Okay, so this is the NZ line. Now, the next line that carries marks is the stability line. So where would the stability line now go? Which points would it pass through?
So go through the origin.
Yeah, definitely go through the origin.
And it will sort of go up, above, go up further and further above the n equals z line, like a curve.
And it will stop. Good. Now they also look for which points it fits in, it crosses in. So for me, the salient points I use when I'm drawing this, I always, when I'm drawing the stability line, that is, to be more specific, I plot a point at 2020.
Yeah.
Yeah. And then another one at 6080. And then another one at 8120.
Okay.
So around about there. I know it's a sketch, but it kind of encapsulates. Yeah.
Yeah.
So if you can remember these coordinates, then it's a bit helpful to plot it, because they do actually look to say when they're marking it, they look to say, is it passing through those points, the stability line?
Yeah. Okay.
And 80, 120. And so now I can pass it through those points. So this here is the stability line.
Yeah.
Good. So now, let's just think about it. This obviously is telling us that generally for small isotopes, let's put a 0 there. For smaller light isotopes, say where Z is less than 20 and N is less than 20, for an atom to be, for a nucleus, to be more specific, to be stable, it prefers to have the same or a 1-to-1 ratio between neutrons and protons. But as the nucleus starts getting bigger, what does it prefer to have more of? It prefers to have more neutrons than protons. Yeah. So we can make a bit of an inference that neutrons actually act like the cement between protons, in that if we think about a nucleus, if I'm increasing the number of protons, I'm also increasing the electrostatic repulsion, so to speak. Does that make sense?
Yeah.
Because now there you go, I've got more protons. So my nucleus is getting bigger. So to reduce the effect of the proximity of these protons together, neutrons are introduced. So neutrons now will, if you like, buffer the two protons, which would have been in very close proximity and therefore created a huge electrostatic repulsion. So increasing the number of neutrons, in other words, the nucleus favors having a higher proportion of neutrons than protons as the nucleus starts getting bigger and bigger, for the reason I've just alluded to over here, to say this then has the effect of reducing the electrostatic repulsion within the nucleus. If they had the same ratio, it would not favor stability. That makes sense?
Yeah, okay. Yeah.
Okay, good stuff. Right. Now, so the elements we see in the periodic table are the ones that are on the stability line. Okay, just the key thing for you to note. Elements in periodic table lie on the stability line. However, we have isotopes that are unstable, and these isotopes can lie either side of the stability line. And because they are unstable, what are they going to do? They are going to try and decay and become stable. And what they'll try and do is they will transmutate. Okay, that's the word I use there, transmutate. onto the stability line by radioactive decay that best suits, or that is the most efficient way of them arriving at the stability line. So because this is a natural process, nature has a way of being very efficient with what it does. It always uses the most efficient means to achieve something, okay? If it is something that is spontaneously happening in nature. And likewise, the decay modes are going to be modes that are the most efficient modes for that unstable isotope to get onto the stability line. So for example, with the guys that are around, say this orangey colored line, what do you reckon would be the best way? What emission would they have to undergo to get onto the stability line? So they've got more neutrons than protons. Through what decay might they favor? Say
beta minus.
Correct. Yeah. So here we're going to have beta minus emitters from this point. Okay. Now we can go further and even look at, well, you can go onto this green line. What about these guys on the green line? What kind of decay will they favor?
Beta plus.
Beta plus, very good. Any others that you can think of?
Alpha, I guess.
Alpha possibly, yeah, alpha possibly. It's an absolute possibility. But there's another one here. So if something was down here below here, it's obviously got less. What has it got less of if it's on the green line? If we just look at the green line, this side. Protons and neutrons. It's got, how does the balance of protons and neutrons comparing? More protons than neutrons?
Yeah, I mean, there are still more neutrons, but there are, in stability line, there are more protons.
You're absolutely right. You're absolutely right. So if a nucleus is proton rich, what other way might it get rid of those protons? So beta plus is a definite way. Very good. What is the other method? And you're right, alpha as well, because alpha takes protons, but which other method?
What's called? Is it what is it? We did it, yes. Is it neutron?
No. Nearly there. It's not that one, because that would be if it was neutron rich. So,
yeah, is it the electron capture?
Very good, Freddie. Yeah. So nucleon is proton rich. It can also decay via electron capture. Good. Now, they like electron capture. They like to see that you can write the equation. We had a go at doing that equation yesterday, so that was really good. The key thing I also want to highlight with electron capture is that during electron capture, it's very important that you state also, if you are having to write anything that's up to 2 or 3 marks about it, it's important you state that also that an X-ray photon is also produced. Any ideas how the X-ray photon is produced?
It's just like the excess energy, like the plus energy at the end.
Yeah, nearly there, and it's tempting to think that way. So if I have my nucleus and I have my electrons like so, this of course, if you like, is swallowed up by the nucleus. Yeah. And then what is emitted? Then well, a neutron is emitted. for one. Anything else emitted?
A photon.
Not quite in this case.
So
Not for this particular for this one, when this interacts with it,
yeah.
so it's captured, yeah. But when it gets captured, it leaves a vacant position. And what happens is that this electron in the second shell takes its place.
Okay.
It is this movement to this energy shell that releases an X-ray photon.
Okay.
So in other words, when the vacant place is filled by an inner shell electron, that results in the emission of an X-ray photon. So it is the vacancy left after the electron has been captured by the nucleus. Good. So here we've also got beta plus as well. The moment when the nucleus gets very, very big, to about 80, roundabout in this region here, yeah. In this region now, the nucleus is actually engulfs the whole this region, yeah, on either side of the stability line. Because the nucleus is very big, the nucleus then tries to gain stability by losing protons and neutrons very quickly, or it tries to get rid of those excess protons very quickly. Beta plus is not a favored method because it only changes a proton into a neutron. So it's not going to really favor making the nucleus smaller. Does that make sense? Yeah. So in other words, the size itself of the nucleus doesn't necessarily change after you emit beta plus or beta minus. What simply changes is the balance of protons and neutrons. That makes sense, right? But the total number is the same. It's just the balance that changes. However, up here, this nucleus is very big and it's very unstable. So it's not really favoring a balance between neutrons and protons. It actually wants to get rid of protons and neutrons so that the size is much smaller. And the most efficient way to do that up there is by alpha emission. Make sense so far?
Yeah, that's all good.
Good, excellent. And because you've done it, it's fairly fresh. Have you covered decay series?
Yeah, so is that like the path that it takes?
Absolutely. So normally when a nuclei is transmutating, it just doesn't change into one daughter nucleus before it is finally firmly stable. It undergoes a series of decays, which could be a combination of alpha, beta, or gamma. Gamma doesn't necessarily change the structure of the nucleus. It simply just reduces its energy. It makes the nucleus more stable. So I'm just going to sketch this very quickly. I think that should be enough for me to illustrate one. Okay, and let's just get this down here, like so. So each of these is one division, okay, both up and the X and the Y. So this would be your NZ. I have simply drawn an enlarged image of it, so to speak, okay? So just to see the different paths that would be taken. So if I was trying to represent alpha emission, well, what would it look like? So if this is my starting point of my nucleon, yeah, so this would be some value here, I don't know, 105 or whatever it is, but there'll be some numbers here, so to speak, of my particular nuclei. So this is starting position. Of nuclei. So this decay by alpha, well, what happens in alpha? My neutron number will go down by 2 and my proton number will also go down by 2. So in essence, my arrow of decay will go in that direction. That would represent alpha emission.
Yeah, okay.
Yeah, you following? What about beta minus? Well, when I've got beta minus, what happens to the number of neutrons? Goes up by 1. What happens to the number of, so I'm just going to do beta minus down here. Yeah, so the number of neutrons, remember beta minus, we've got a neutron turning into, a neutron turning into a proton plus so the number of neutrons goes down by 1, the number of protons goes up by 1. Make sense?
Yeah.
Good. So that one would point down this way. And the reverse would be true for beta plus then, wouldn't it?
Yeah.
So what you'd have is you'd have a series of steps where it shows it's decayed by alpha, then it may decay by beta, in which case your line would zigzag to that form, and then it may decay by alpha again, in which case you'd get another alpha line, yes, and you'd keep on following that line until you got to your most stable daughter nuclei, which might be a great granddaughter nuclei by that stage. So far, so good?
Yeah.
Excellent. All right. Now, one thing to just tackle on. So if we're looking at an NZ graph, and we had to explode this graph into what we just had before and create a grid, what you would see then is that the beta minus would be doing this, trying to get to the stability. That was that diagonal line. Yeah.
Yeah.
And the beta plus would be kind of doing that. I know my scale is not the best to get onto the stability line. Okay. And the alphas would be doing that to get to the stability line. So it's more efficient, much quicker way to get onto the stability line. Okay, good. So memorize this. Have a go at trying to draw it from memory a couple of times. And be able to label where all the regions are. Superb. Next, we're going to look at nuclear energy levels. Do you remember looking at nuclear energy levels?
Yes. Yeah, I think so.
Good. So just as we have energy levels for electrons, we also have nuclear energy levels or energy levels within the nucleus. How was this discovered? This was not known, but thanks to radioactivity and understanding of actually how gamma emission comes about, that is how nuclear energy levels got to be discovered. So how does gamma emission actually take place? Gamma emission normally takes place after alpha or beta emission has happened. So gamma emission normally takes place after emission of alpha or beta. Yes? Mm-hmm. Why does it take place after emission of alpha or beta? Well, essentially what happens is that even after the new daughter, when the new daughter nuclei is formed, its nucleus still has a lot of energy. So it tries to get rid of that energy. And the best way to get rid of that energy is via alpha emission. Okay, so we're going to say here that daughter nuclei formed is usually in what we call an excited state. So it's not in its ground state. So remember when we were looking at electron energy levels and we had a ground state, right? And then we had all those other different excitation levels, which were the different energy levels. Remember that. A very similar thing exists as well for the nucleus as well. So daughter nuclei formed is usually in an excited state. So to get rid of this energy, so to get rid of this energy and attain stability, it emits a gamma photon. or photons. It all depends on the energy levels within that nucleus. So if we look at, say, the decay of magnesium, just as an example. Now, this, by the way, normally happens a very few seconds after alpha or beta has been emitted, then the gamma emission follows very, very shortly after. So they happen pretty quickly, one after the other. So if I've got magnesium here, now this is a radioactive isotope of magnesium, okay, magnesium 27. This decays into aluminium. So what we're drawing here now is an energy level diagram, a nuclear energy level diagram, which is worth being able to know how to draw, but also interpret, okay? So that's my magnesium, okay? And then my magnesium now goes, I show an arrow here. My magnesium then transmutates or decays into aluminium 2713. And this is via the emission of a beta minus particle. So I've labeled that. Now, there will be an energy level associated with the aluminium at this point of its nucleus. An energy level associated will be given, or they'll tell you, so you know what to label. So this is just an example, 1.02 MeV. So what it can do, the aluminium, it's not quite in its ground state. So the ground state is somewhere here. And this is labeled with 0 mega electron volts. So the aluminium can go from 1.02 mega electron volts to 0 mega electron volts by releasing a gamma photon. But because the energy levels within the aluminium itself, it could do this by firstly releasing or lowering the energy state through root 1, which is at a slightly lower energy, which we could call 0.8. I don't know why I said 3 there, but there it is. 0.83 mega electron volts. That's just an example. Okay, so this is here our starting nuclei. Okay, so it could then, of course, go on to from 1.02, go to 0.83, release a photon that corresponds to the energy difference there, and then after that, drop down into its zero state. So what I mean, in other words, is that this, this magnesium is decaying, in essence, to either form aluminium with an energy level of 0.83. So it releases a photon corresponding to this purple line when it goes to its ground state, or it can be released at a very high energy state and release 2 photons or 1 photon if it goes directly. So the photon or the spectrum associated with aluminium going into its ground state is composed of, therefore, how many different paths? 1, 2, 3. So these are the 3 different photons you could expect, gamma photons you could expect when aluminium goes down into its ground state. That make sense?
Yeah. So, but what one thing I don't get,
yeah,
is, so you know that pink arrow?
Yeah.
How can it get to that energy level without already emitting a photon?
How can it, sorry, get to this?
Yeah.
Oh, it's confusing. I know, I didn't make it very clear. Thank you for giving me this chance to make it even more clearer. So because the nucleus of aluminium has got different energy levels in it, yeah?
Yeah.
When it decays, the aluminium will be in its most excited state.
Yeah.
This is most excited state. So to go to the ground state, the nucleus can either firstly lose this photon in blue and then drop to 0.83.
Yeah.
But it's still not going to be stable. And then eventually it's going to lose a photon with 0.83 mega electron volts and eventually get down to its ground state.
Yeah.
Or it could very possibly be at 1.02 mega electron volts and drop directly to 0 mega electron volts.
Okay, so there are only really two paths it can take.
Well, there is this one here, which is directly from there to there.
Yeah.
This is photon 1. In other words, what I'm saying is that there are 3 different photons that will be emitted, depending on which route it takes.
Yeah, okay.
Yeah, so these are the 3 different photons, 1, 2, 3, that are associated with the decay of aluminium. Sorry, not decay, the de-excitation of an aluminium nucleus.
Okay, cool.
That makes sense, right?
Yeah.
Excellent, good stuff. So now, the technetium generator. So the technetium generator is one that is used in tracing, and it's one the examiner likes asking about. Now, what does this look like? So what happens is that we have molybdenum, 99. Now, they'll give you these values. Don't worry about them. You don't have to memorize them. They'll give you this information. So you have molybdenum, 99. This then decays via beta minus emission and forms technetium 99. Now, technetium 99 is used as a radioactive tracer in human bodies because it's got a very short half-life. Now, interestingly enough, this technetium that's formed is what is known as metastable, because it stays excited, yes, for a very long time before releasing a gamma photon, which is very unusual. Because remember what I said, as soon as beta or alpha emission follows, a gamma particle is then, a gamma photon is quickly released after that to make the nucleus stable. But in this case, technetium 99 does something really strange. It stays in its excited state for a very long time, and that is why we call it metastable. Because it's kind of stable, but not really stable. And this is molybdenum 99. So this is an exciting state, and this will have a certain energy level associated with it. When it then finally de-excites and goes into its ground state, a gamma photon is emitted. By this stage, this metastable, so you are injected with the metastable version, and in 6 hours, the gamma photon is released. So 6 hours is long enough for the tracer to move through your body and for measurements to be taken. Now, molybdenum itself has got a very long half-life, or longish half-life. Yes, about, is it 72 hours, if memory serves me right? So it allows it to be transported to the hospital without it having started decaying. So that is the beauty of this, or using molybdenum. It kind of, it works ideally. Where is this obtained? This is obtained from nuclear reactors. Obtained from nuclear reactor waste. Okie dokie. Anything else I should add on there? More than, yeah, I'm just going to say ground state here. So we'll go, actually, let's break it up a little bit, and let's break it up a little bit. And see if we can bring in something to, just a moment, I'm just trying to see if I can find something here. Right there, yeah. I think it'll be worth just assessing that you are okay with some elements and ground states and such, because let's try and see if we can crack through this one. So they like asking these ones, so it's worth knowing how to do them. So I will, there we go. I've got this multiple choice question here. I'll make it a little bit bigger. Just to bring the concept to life a little bit more.
Okay. Okay. Hi. Yeah, okay, I'm sure that's more. Okay. Okay, I've got an answer.
Good, go for it.
Oh, is it B?
It is B. Well done.
Yeah,
Excellent.
I figured out the shortest wavelength first because I just got confused.
Oh, good. You got that. Oh, yeah, it is B. Yeah,
Is
tell
it?
me, what was the longer way? What route did you take, rather?
No, it was. I just got confused because when I read longest wavelength emitted, I just figured out the highest frequency was obviously the lowest frequency.
Very
Uh,
good. And so
so
obviously the least energy, so the smallest energy difference, isn't it?
yeah.
Very good. How did you work out the number of discrete wavelengths?
So I just basically just drew the. So I drew out the 4 lines.
Yeah.
I basically just went through each path, each possible change.
Yeah. What about if next time they give you 1, 2, 3, 4, 5 lines?
Oh yeah, is it would that be is it factorial?
It involves some factorials there. So what would it be then for 5 lines?
Um 24.
Not quite. It'll be way, way,
Um
way less than that.
um
Don't worry, give you a little trick for next time. Yeah. So however many the number of lines, so number of lines, and how many are we choosing from? So we had 4 lines, and we only want to choose any 2 sets of lines. Yeah. So this gives us 6. So if we have 5 lines and we're choosing only a set of 2 combinations, so that would give us 10. That'd be 10 for that one.
okay.
Yeah. So
Yeah.
this is a useful one, just in case they give you, like I'm saying, 5 lines. You'll be more certain if you use that than if you try and draw different colored arrows. You might miss 1 or 2. Okay.
Yeah.
Okay. Excellent. All right. So that is that on that one. If you've looked at a few questions, these are the type of questions you may be asked, but also sometimes you may be asked to draw this diagram where you are given the information and you'd have to show something like this. But I don't think you'd struggle. You've not struggled. You've managed to change this successfully to joules because you had to do this question. So I'm not too worried there. I'm impressed that you've got that pretty quickly. Excellent. So very quickly then on to finalize the very last aspect of this is to talk about what are the ways used in determining nuclear radius. What are the methods of determining nuclear radius? What do you know about the methods? So one, can you remember the first one? The first
Yes.
method that was used.
Yes. Is it R equals as it's like R equals R naught.
Oh, that one, yeah, the theoretical one, which is R equals R naught A to the, yeah. So in terms of this one here, of course, you have to then work out what the rate or what this R naught is, yeah. But the other method or 2 methods that you need to be aware of, importantly, is the alpha scattering. Yeah. How is that used to calculate the nuclear radius? Well, alpha is positively charged, and there's your nucleus, which is also positively charged, and we used the distance of close approach. Now, how does the distance of close approach work? Yeah, we know that if this has a certain, oh gosh, we know that if this has a certain kinetic energy, EK, when it gets to the point where it now faces repulsion, so that distance, at some distance, it's going to be repelled. So let's imagine it stops at that point. What happens to all this kinetic energy that it had? what is it transferred into?
Potential energy.
Correct. So at this point, EK equals 0, EP equals max. Yeah?
Yeah.
So how was then this used? Now this involves electric fields. Now the examiner says electric fields are not going to be in the exam, which I don't know. They say they could bring it in, low tariff, okay? So how do we find, if you like, what would the electrical potential be if these were separated by a distance r? Now you've not done electric fields, have you?
We did do them.
Oh, that was before the advanced information came out.
Yeah.
Okay, all right, okay. So in which case then, if I say this has a charge Q and this nucleus has a charge Q, obviously positive in each case, yeah, it's going to have a bigger positive charge because of a bigger nucleus, then the potential energy would be plus Q that over 4 pi epsilon naught, yeah,
Yeah.
over R. Would it look something like that?
Yeah.
Correct. Yeah. And then this potential energy here, remember, is going to be made equal to the kinetic energy, because all the potential energy has gone into, sorry, all the kinetic energy has gone into the potential. So this value must be equal to the kinetic energy. So if you know the kinetic energy of the alpha particle, you can work out this distance, because you know what the charge of your nucleus is, your gold foil, you know what the charge of your alpha particle is, and these are known constants.
Yeah. Okay.
Does that
So
make sense?
in the electric potential equation,
Yeah.
there's just one Q. What does that mean?
In the, sorry,
in the data sheet, it gives the equation for electric potential.
Yeah.
And it says that it's just Q.
It's me that's not looking at the data sheet. You're right. It would be plus
Over.
Q. You're the one who's right. I'm not looking at the data sheet. I confused my formulas. I was confusing QQ,
yeah,
4 pi epsilon naught r squared. Yeah, for the force between the two. Sorry.
So is that the Q of the small of the alpha particle then?
So it would be, yeah, because we're looking at the potential energy of the alpha particle.
Yeah, okay.
So we're saying it's the kinetic energy of the alpha particle that's transferred into the potential energy store of the alpha particle. That's why I've crossed out the big Q.
Okay, so does the charge of the nucleus not does that have no effect on the potential energy of the alpha particle at a point in its field?
The potential energy of the alpha particle is independent.
Yeah, okay.
Of the charge.
Okay.
Because the system, if we looked at this as a system, this system is only exchanging energy between its potential energy and its kinetic stores. It's not exchanging energy, if you like, per se, with any other charges around it.
Yeah, okay.
Okay, if that makes sense. Good. So what is the, so this is the formula then that you'd use, Q over 4 pi epsilon naught R. But if they bring it in the exam, they will give you this. They're going to tell you to say, use that formula. I'm certain of that. Yeah, especially if they've said it's low tariff. Okay, good. So what's the disadvantage with this method? You don't quite get the radius of the nucleus. You only get the distance of closest approach. So it only gives you an indication. So this alpha particle will not touch this nucleus.
Yeah.
So it only gives you an order of magnitude.
Yeah, okay.
Doesn't give you the precise, only gives you an order of magnitude. And it's based on probability, because for one, you're assuming that this alpha particle is bombarding this nucleus head on.
Yeah.
If they were not head on, then this equation doesn't apply. So it's based on probability. It's a probability-based type equation, okay? So it relies on probability. And the other method we have is electron deep inelastic scattering. This is also like, these are also inelastic scatters, yeah? Now, electric deep inelastic scattering, what does it involve? It involves bombarding, again, thin metal, but this time you're bombarding it with electrons. Now, these electrons are fast moving, so they've been accelerated through a very high PD, potential difference. So if something is moving like an electron, what can you remember? What does it possess? It possesses wave-like properties, and it will have an associated de Broglie wavelength given by lambda equals h over p. So this here will be the de Broglie wavelength of the electron. Make sense?
Yeah.
So when it then interacts with matter behaving as a wave, because its wavelength is roughly of the order of magnitude of the size of a nucleus, we get a diffraction pattern. And this diffraction pattern, in other words, very similar to the alpha scattering, I'd have a detector. And I would move this detector through different angles. And what we observe is we observe a pattern that looks like so. Central maxima, minima, and then it dies off. So on this axis here is intensity that we observe, and on this side would be angle. Okay, where that would be 0, and this of course would be angles for theta plus theta, and this would be the minus theta angles. Make sense?
Yeah.
By using this first angle here, where this first minima occurs, we can work out, there's a relationship that says that sine theta, you don't need to know this, you'll be given it, is equal to 1.22 lambda over 2r, where r is the radius of the nucleus. This here would be the de Broglie wavelength of the electron, this value here.
Well, sorry, why was there a second like dip in the...
Now the reason why you have this, it's all to do with waves. So if you remember, this is now us visiting single slit diffraction.
Yeah, okay.
Absolutely, it comes from that. And the theory behind this, why you have this second here, is because when diffraction happens, at that point on the wave front, each point on a wavefront acts as a source of secondary wavelets. And it is these secondary wavelets that interfere with one another. So for instance, if I have a most unusual thing indeed, if I have a small slit and I shine red laser through it, very tiny slit. So that's my slit. That's a red laser, and I have a screen on the other side. What pattern do you reckon I observe on my screen? Most people would say you see a red dot. Yeah?
Yeah.
But that's not what you see. What you see on your screen, so now if we actually looked at this screen from that angle, what you'd see on your screen would be, you'd see this huge disk, very huge disk, and around it, you'd see rings. Now, the thickness of this part here, if you call this T, this here would be 2T. And these rings carry on, actually. You're going to see more of them. Bizarre.
Yeah.
Why does that happen? That is because diffraction is happening at this point. In other words, if the wavelength is of the same order of magnitude as the gap in which it is passing through, then if these are wave fronts, so let's imagine that these are wave fronts and this is my ray. So these are the peaks of the waves. We're now thinking about it as a wave. So if this is my opening, and we can see that the opening has roughly about the same size as the wavelength. The wavelength of my wave is this. This will diffract. It will spread out. And it is this spreading out that creates this pattern. So what I said before was that each point on these wave fronts, this is a principle known as Huygens principle. They've taken it out from the spec for some odd reason, but each of these will act as a source of secondary wavelets, each point, and there are infinite points, by the way. So I'm just trying to help you visualize this, okay? Likewise, on this wavefront, each of these here will also be other sources of what we call secondary wavelets. So these I will call secondary wavelets. So these secondary wavelets have the same frequency as the actual source and also the wave that's being propagated. And these secondary wavelets, remember the phenomenon of interference?
Yeah.
Good. So interference of secondary wavelets is what creates this pattern. And so if you had something diffracting through a single slit, this is what you see. Now note in your exam, they want you to be able to draw this diagram. So this is profile for single slit diffraction. I've digressed a little bit here. I've gone into waves just to remind you of some key aspects for single slit diffraction. So this here is your central maxima. This here is your first minima. Sorry. And that's your first minima. The width of this here must always be 2 times the width of the subsidiary minima. So these here are known as subsidiary minima. So long story short, the reason why we get this pattern is because secondary wavelets interfere with one another and therefore create a pattern that is of a similar type to interference. Now remember to double slit interference. With double slit interference, what was the pattern like? If you remember, it was this. And in double slit interference, these widths are the same. And this is where you have 2 sources of waves. So what I'm saying is this pattern looks very, very similar to that, in a sense. Now, the reason why this is dying off in double slit interference, double slit. So this is your light source coming in here. There will be the width of each slit creates an envelope. Now this envelope is not visible, and this envelope, this is the pattern of the single slit pattern. I won't go into it because it's quite complex. This would be a topic on its own to cover, but this is something that a lot of students find hard to explain when dealing with waves. Okay, so that is a reason why, Freddie, you get this diffraction pattern. It's behaving like a wave, and so you've got little sources of secondary wavelets, and they're interfering to give you that pattern. Now, of course, this method is more accurate. Why is it more accurate? A lot more accurate. Why do you reckon this method of deep inelastic scattering using electrons is more accurate than alpha scattering?
Because because I mean, I guess like the first one, just there's a lot more. How do you actually find the radius from this electron scattering? Like you can.
So you use, that's a good question. This is the
Oh,
formula.
use that one. Sorry, yeah, use that equation.
Yeah.
So I guess there's no like it just, I feel like it just is better. Like the first one just isn't great because you have that gap in between.
Yeah, you're right. You're absolutely right. Was here, well, an electron has got what charge?
Minus.
And a nucleus has got what charge?
Positive.
So we're going to have the same problem with having a gap.
Yeah.
Between the electron and the nucleus.
Yeah, when
you wouldn't have that problem. That problem will not happen. So in other words, here we're saying, why is it better? Because electron is attracted to the nucleus.
Yeah.
And matter of fact, the electron can pass through the nucleus. Why can it pass through?
I didn't. Why can't it pass? Because like it's good. It's because I know this isn't like the right phrasing, but like it has it's a good like escape velocity from like.
Oh, I see where you're coming from. Yeah. Like it's got enough velocity that it can escape the pull. I see where you're coming from. Yeah, and no harm in thinking that way. Yeah. But the real reason here is this brings us back to some year 12 theory. This guy here is a lepton.
Oh yeah.
And so not affected by S strong nuclear force.
Yeah.
Unaffected by strong nuclear force. So you get a far more accurate picture on the size of the nucleus.
So what would happen, like theoretically, when the electron actually like goes to the nucleus and like hits it straight off?
Yeah.
Like surely the electrostatic force is still there.
Correct. But
so it just doesn't stick.
So in other words, also remember that the electron has got kinetic energy.
Yeah.
Absolutely, well done. So it's got kinetic energy. So maybe to think about the analogy and understand it. And I know because we're now in the nucleus, it's very hard to find a macro example in real life to try and see what happens, but we can get some ideas. So it's moving at very, very high speed. Yes, for one, because it's been accelerated through a high PD. So it's got a lot of kinetic energy. So even when it gets attracted by the nucleus, it will not be stopped by the nucleus.
Yeah.
Does that make sense? So you've got two magnets.
That. Yeah, I get that. Yeah.
Good.
Because,
so what then happens now? This is when it starts approaching the nucleus, of course, then what happens to its, if you like, its potential energy? It's being attracted towards the nucleus.
Yeah.
But key thing to note here is that the electron itself is pretty tiny. And the way to think about this now is wave-particle duality comes into play. Then it gets pretty tricky to explain in its fullness. And even I, at some point in time, will get out of my depth when it goes too deep into the nucleus. But from the basic point of view, when it interacts with the nucleus, the electron will behave as a wave.
Okay.
While it's being attracted by the nucleus on its way en route, before it even meets a nucleus, it will be behaving as a particle.
Yeah.
So at the point of interaction between the nucleus and the electron becomes a wave.
Okay.
So instead of you physically thinking about it as a little particle, tennis ball, going through the nucleus, don't think about it that way.
Yeah, okay.
And
Sure.
it's really strange because now we're getting into the realm of spooky physics. How can something that was a particle, how would it know to change to become a wave the moment it encounters a nucleus?
Yeah.
What mechanism is making it know, so to speak, to become a wave and not to be a particle? Because if it was behaving as a particle and it's a small particle at high speed, and the nucleus was also behaving as a particle, what would we expect? We'd simply expect the electron, and the nucleus has got a very high charge, would simply expect the electron to be attracted to the nucleus, and that's it. And the total momentum is shared, and then the nucleus and the electron fly off in some direction the electron was traveling in, assuming the nucleus was stationary. But we can't think about it that way, unfortunately.
Yeah, okay.
Yeah, but it's a very, very, very good question, Freddie. So wave particle duality comes into play, but at least it's good that we've touched on this just to remind us that electrons aren't affected, because they like asking this and because it's strongly linked to some year 12 stuff. So they like throwing that in. Right, so now energy and mass. We're done with that aspect. So energy and mass. And I can make a start on this here. Energy and mass. Right, energy and mass. So what is this all about? What am I, straight to the point here, we are referring to E equals mc squared. So energy and mass equivalence. So the great Einstein came up with this, and he postulated that energy is equivalent to mass. Of course, this was something that taken time to get to, firstly from the point of view of understanding photons first. So the photoelectric effect was, if you like, one of the biggest breakthroughs. What was the photoelectric effect? A very big breakthrough. Well, it was the first time then that we started thinking of wave-particle duality. Okay, wave-particle duality. At that point in time, the physics community realized that actually waves can also behave as particles. Likewise, de Broglie was also able to show that matter can also behave, meaning particles can also behave as waves. Then another thing that was a very big discovery was the fact that energy in atoms is quantized. Now, not only is energy quantized, but charge is quantized as well. And the smallest quantum of charge is the charge of an electron, okay? And then there was born nuclear or quantum physics. So from quantum physics led to the birth of this equation, E equals to mc squared, all right? So what does this really mean? This simply means that if I have got a value in energy, I can think about it as having an equivalent mass. Or if I've got a mass, I can think about it as having an equivalent energy. The currency of connection, or the, if you like, the constant of connection between the two is c squared. Yeah, speed of light.
Yeah.
So what does this help us explain? Firstly, if we have, or if we just look at a nucleus, and we take nucleons on their own, separated, and we compare this to the bound nucleons, these will always be of a lesser mass. Why? Well, that's because some energy has gone into binding them together.
Yeah.
Okay, so these are free nucleons. So the deficit in mass, the mass difference, delta M, will give us the energy delta E that is, if you like, released.
Yeah.
In binding these, energy taken in to bind these nucleons. So if I unbind these nucleons, what should I expect to see? I should expect to see a lot of energy being released. Why does it take a lot of energy to bind nucleons? Well, work has to be done. Work has to be done. Work has to be done to bind nuclei. You following so far?
Yeah.
Good. So therefore, if I just think about firstly the strong nuclear force, where is this work coming from? Well, work is being done by the strong nuclear force. It is done by the strong nuclear force. Now, even though it's over a few femtometers, the strong nuclear force is very, very strong. Yes, to the point that even though it's just bringing nucleons over a few femtometers, a lot of work in the region of mega electron volts is done. And it is this amount of work that is lost from the system, so to speak. So if I wanted to unbind these nucleons, I would have to what? I would have to put in energy. Does that make sense?
Yeah.
Excellent. Okay, so I'm going really, really quickly about this. So if, for instance, I wanted to look at, say, any decay equation, just a decay equation, alpha decay, just to say in all decays, energy is given out. So what are the decays we've got? We've got alpha, beta, gamma, and of course, we've got electron capture. So if I just look at alpha emission, yeah, so if we've got, well, I'm just going to make it, should I use, yeah, I could use X, A, Z, and we release an alpha particle, A minus 4, Z minus 2. Generally speaking, the way we represent this is that we write this alpha particle on this side of things,
Yeah.
plus energy. What I'm saying is here, the individual constituents in mass of these things which we call particles. This will have a bigger mass than that. You following?
Yeah.
Why? Because there's energy, and energy this side accounts for mass as well. Into the nucleus, delving into the nucleus and the strong nuclear force. So, binding energy. What do we mean by binding energy? This is one that they like to ask as a general definition.
Yeah.
So we talk about binding energy. So it is a work that must be done. Work that must be done to separate a nucleus into its constituent neutrons and protons. Now, do you reckon this definition is enough?
Yeah, I don't know.
It looks enough, doesn't it?
Yeah.
And you generally get marks for this, but just note here that to separate a nucleus into its constituent neutrons and protons that do not interact.
Okay.
because you can separate the neutrons and protons, but if they're within close proximity of one another, they're going to be interacting. So in essence, in theory, these protons are separated by a distance of infinity.
Yeah.
Okay?
Okay.
So that is what binding energy is. Now, this concept we looked at here before, we were looking at this concept of mass defect. So what would you say the mass defect is?
I guess the change in mass with change in energy.
Okay. On more specific, more specific, we say that this is the difference. So here there's a difference in mass.
Yeah.
So this is big M, this is small m. So M minus M would represent the mass defect. That's the lost mass. So it's the difference in mass between the uncombined constituent, or rather constituent nucleons. It's the difference in mass between the uncombined constituent nucleons and the bound nucleus. Does that make sense? So
Yeah.
difference in mass. Yeah, so far so good. And that is
Yeah.
what we call the mass defect. Sometimes, they like to ask you to write equations for this mass defect business using notation. So just to note, delta M would be equal to ZMP plus A minus ZMN minus the mass of the nucleus. Does this all make sense? Well, this here, A minus Z, will be the number of neutrons. That will be the mass of the neutron. Z is the number of protons multiplied by the mass of the protons. So this is the big M, where these are neutrons, these are protons. So far, so good.
Yeah.
Good. So once you know what the mass defect is, you can work out what the binding energy is. So the binding energy really is a measure also of the potential energy of a nucleus. Is a measure of the potential energy of our nucleus. Okay, now just think about what happens from a rather more intuitive perspective. Think about a well. Something that looks like this on both sides.
Yeah.
And let's imagine a particle. Let's just imagine a particle of mass. We're just going to think about it in terms of mass. Okay. So as I roll this towards the lip of my well, what's happening to its potential energy?
It's increasing.
Increasing?
No, sorry, decreasing. Yeah.
Decreasing? Let's think about it again. I'm rolling it up a hill. It's going further up. What's happening to its gravitational potential energy?
It's increasing.
You're right. It's increasing. And it gets to a maximum when it's at the top. Then it drops in this well. What happens to its potential energy?
It's decreased, but yeah,
it's decreased, isn't it?
Yeah, it has decreased. Yeah,
it's up. You're absolutely right. Now, a very similar thing happens as well. I can think about these as having two particles instead of one that I'm rolling this time up the hill. But we're going to think about these in terms of charges. And think about this hill here as representing the coulombic repulsion. And think about this well here as representing the strong nuclear force. Yeah?
Yeah.
So as I bring these two nucleons together, I didn't draw it quite right. So let's imagine that one of them, this red one, is at the top. It shouldn't be down here, sorry. So as I bring two nucleons together, as I bring this positive, let's imagine that they're all positive, will make life easy. The repulsion is increasing. So what's happening to the electric potential energy of my particle? It's increasing.
Yeah.
Yeah, good. However, when they reach a certain proximity towards one another, the strong nuclear force kicks in, because it kicks in when the radius is, or when the separation is less than 3 femtometers.
Yeah.
So when it's less than that, it binds them together and brings them down into this well. So now I've got two of those particles bound together due to the strong nuclear force. The energy they now have here is now a negative potential energy. When they were repelling, they had positive potential energy. Do you follow that?
Yeah.
Good. Why is the potential energy negative here?
Well, because they're attractive. Like they're attractive. Attracting.
Nearly there is positive, due repulsion, positive potential energy. Nearly there, nearly there. Now you see this question in gravitational fields, generally where they draw, I don't know, some planet, and then you're given some, or yeah, you could have something at an orbit or whatever, and they might say the potential energy is minus 350 kilojoules per kilogram. And they might say, why is it negative? How do you answer that one? It's a very popular one, that one.
Wait.
So I'll help you out on this one. And it's a standard response, but hopefully it will make sense as well. And I can explain if it doesn't. But because energy has to be put in to the system.
Yeah.
That is a reason why. So what this means, if I'm telling you that the gravitational potential at a point is minus 350 kilojoules per kilogram, what that is saying is that to take a 1 kilogram object to infinity, you have to put in 350 kilojoules.
Yeah.
So in other words, and this confuses students quite a bit. I know it's a very confusing concept, so I'm going to try and make it as easy for you to understand. So in a bound system, now what do I mean by a bound system? I'm talking about a system where forces are attractive. In a bound system, the potential energy is always negative. Why is it negative? Because you have to put in work to unbind the system.
Yeah.
Does that make sense? And if you're
Yeah.
putting in work, we always use a positive connotation. We always use a positive notation
Yeah.
for work being put into a system.
Yeah.
So in other words, very basically, if this was a depth of 1 meter and you had a ball here on top of the surface of the earth, what's its gravitational potential here on top? Let's imagine it's 1 kilogram and we take G equals to 10. Here, it's 0 because I'm measuring the height from here and this is my 0 height. When this ball now drops into the well, what's its gravitational potential energy here? Well, it's minus 10. What's this telling me? The minus figure is telling me to say, to bring it back up to the surface of the earth, you're going to have to put in 10 joules.
Yeah. Okay.
Yeah?
Yeah.
That's why we use negative energies for potential energy. So if ever you ask that question for gravitational fields, literally, this is simply because energy has to be put in. In other words, you're going to say the system between the planet and the star is a bound system, i.e. forces are attractive. Therefore, to separate the two, energy would have to be put in. And the energy that would have to be put in this case, they'll give you a value at times, you'd have to quote that value.
Yeah. Okay.
Okay, good. Right. This can be very tricky. We're going into very tricky environment here with binding energy. So I'm really just trying to make sure that you understand the basics because it can be very, very tricky, Freddie. But I know that you are capable of understanding it. So I'm just trying to make sure that I fill in all the gaps of what students tend to find a bit tricky. We're not so far from undertaking binding energy calculations, which is going to be sort of the tail end with fission and fusion. But I think we've gone at a good pace. We're going at a steady pace. We couldn't wouldn't have been worthwhile going much quicker because I wouldn't have had the opportunities to give you all these final little nuances you need to know. Okay.
Yeah.
Rightio. Do you have any questions over what I've just discussed? I could see that you had a bit of a puzzled look when we're talking about these negative potential energies.
Yeah. No, I think I'm slowly getting a grasp of it. So would it require 350 kilojoules per kilogram to get it to infinity?
Correct. And only
point.
when it's at infinity, because you have to remember that only when it's at infinity will there be no force acting on it. So if we remember, F equals G M over R squared, or for gravitational potential, yeah, that would be minus GM over R. Well, you'd have the big M there as well. Yeah.
Yeah.
But if this R is infinity, then the potential will be 0.
Yeah.
So in other words, we need to take something all the way to infinity for it to have 0 potential energy. Only then will it not interact with any with the mass it was next to.
Yeah.
Makes sense?
Yeah.
Good. It's the reason why negative numbers are used.
Yeah. Good.
Righty. So you go back, Freddie, on the 19th, don't you?
Yeah, so I go back on the 19th, but basically I've got next week.
Yeah.
Starting on Sunday, I've got a revision course at school.
Okay.
So I'm out for that week. And then
that's next week. Is it from like Monday or something?
Yeah, it's from like Sunday, I think.
From this coming Sunday.
Yeah.
Okay. Wow.
So we've got an hour left, don't we, at the moment? Of lessons.
No, I was only paid for 4 lessons.
Okay. So I thought it was.
So remember, it was if it's for 9 lessons, you get the 10th lesson free. Yeah.
Okay, so I thought it was if you do 8 hours, you get the 9th hour.
I see what I see your understanding there. That's fine. That's fine. Okay, I didn't make it clear. I'll take blame there. I'll take blame there to say you get another hour. That's fine. I take blame. That's fine. Yeah. I see
Okay,
why
I
you read
appreciate
it as
that.
8 hours and then the ninth. That's fine. Yeah, I'll happily do that for you, Freddie.
Okay, I appreciate that.
An hour.
So
Yeah, that's fine. That's
in
fine.
that case,
Yeah.
can we do an hour tomorrow? And
Yeah,
then
and this is where I wanted us to have a quick discussion. The best thing that would work for me, because if I'm unfortunately having to go on some family excursion tomorrow.
okay.
So the thing that would work best for me is either we can squeeze in that hour. It's all up to you, but I know if you've got school on Sunday, you might want to squeeze that hour in during the week sometime, wouldn't you? Would that work? Because you're not going to
Yeah.
be at school the whole day. Would you be at school?
No. So I think it ends like 4:30 each day.
Yeah. Okay. Oh, you finish at 4:30.
I think it's something like that, or 5 or something.
Oh dear, that's a long day. Right. So I could provisionally, well, I'm gonna have to rule the Friday and the Saturday out, really. But then I know that the Sunday you're at school.
Yeah,
So you
I
could,
just need to double check if I'm at school on the Sunday.
all right,
Um,
double check that, Freddie. Send me a text, and if you're
yeah.
not, I'll do the hour with you on the Sunday.
Okay.
And if you should wish that we do it in the week, I'm still not going to school until the 19th of April.
Yeah.
Yeah.
Mm.
So literally, I will still have next week and part of the week after.
Yeah. I don't think we would do anything during that week, but I think it ends on Thursday.
Okay. So
So I
after
go
that, we
back on
can,
the Wednesday.
yeah, after that, we can pick up pieces, because if it ends on Wednesday or Thursday, just let me know. And then I'm obviously going to give you the 1 hour. And then if you want us to finish off magnetism and such, then let me know. And then we will have, possibly, depending on how much days you have after you finish next week, we'll probably have from Thursday till the Sunday if you wish, or till the Monday if you wish, to
Yeah.
pick up some times for other lessons if you so wish to.
Okay, cool.
Does that sound good?
Yeah, sounds good. Yeah, so
Brilliant, Toss.
so I guess we'll just find the time for that extra hour.
Yeah. It's just that let's sort out the extra hour. Let me know once you've had a look through your schedule, yeah?
Yeah,
And
sure.
then I'll throw that extra hour in for you. Very good.
Okay,
No
brilliant.
problems. And then that extra hour should be enough to tie up the loose ends outstanding, so that then when we start the new block, we can start off on magnetism.
Yeah.
Does
Okay,
that make
great.
sense?
Yeah, brilliant.
Brill.
Okay.
Right. Have a lovely afternoon. Thank you so much for understanding today. And I look forward to seeing you next week. I know it's going to be very hard one for you. So try and pace yourself. Yeah. And keep doing all the good stuff that you're doing. And don't forget the music as well.
Yeah, okay.
You didn't tell me what music you're into, Freddie.
Yeah, I do a lot. I into loads of types of music. I play a lot of classical. I also play a lot of jazz.
Oh, good.
So, yeah. I'm really into
Fantastic.
that.
Well, keep that up, because you never know when you go to university. When I was in university, I used to run a band, and I played at all the Maybowls for the whole 4 years. And even after I left university, my band still used to go to the university and play. So keep that up.
Yeah,
Yeah, you never know where it takes
that's
you.
cool. Yeah.
All right. Have a nice one. Yeah.
You too. Yeah. Cheers.
Cheers.
Thank you.
Bye now. Bye.
Bye.
Bye.